Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to go ahead and figure out how concentrations affect the chemical potential of a system by looking at the Nernst equation, which really is just a way to rephrase what we've already seen with Gibbs free energy. So as we've seen before, we can relate Gibbs free energies to potentials, but one of the things we can do is use this to crib a little cheat sheet from what we've seen before. So we know that the favorability of a reaction depends upon the concentrations of the products, the reactants, using our reaction quotient. So that's at instantaneous concentrations. However, what we can do is try and turn this into potential by using this relationship that our Gibbs free energy is just equal to the negative of NFE. So we can go ahead and do that for both our non-standard state potential. So again, this would be the potential that I would measure of a system that has concentrations that aren't 1 molar, and the potential of that standard state conditions. And again, Q will really tell me about the difference in between those. So one of the things you may have noticed by plugging in this expression, we've got a lot of redundant terms. NF shows up twice. Let's make it show up once. We can divide both sides by negative NF, and then we just pop all those extra unwanted terms onto the third term. He's carrying all the baggage. So what we're really seeing is we can relate the potential at any given concentration of a system to that standard state potential we can go look up in a table. And then we subtract out the difference where we've got R, which is our ideal gas constant, T, the temperature of the system, N, the number of electrons being transferred by the system, and F is, again, just that unit conversion of the Faraday constant. And then all times the natural log of our reaction quotient. So this lets us figure out what our exact potential is at a wide variety of concentrations. Now, one of the really useful things here is the ideal and Faraday constants are, well, constants. So they won't change with systems. So we can go ahead and consolidate our R and our F together into a single constant. And what's even more useful is since most of our measurements are made at room temperature, temperature can come in and hang out too. So it turns out at room temperature, we can gather together our ideal gas constant, Faraday's, and again, the temperature of the system to a single value of 0.0257 volts. And this is going to make things a lot easier as you don't have to calculate out everything the long way each time. And this again lets us relate that instantaneous potential to the standard state. And again, all we need to know then is the number of electrons being transferred and the amount of products and reactants in the system. So this will let us figure out how we can look at either a cell reaction or a half reaction, again, at any given concentrations. So let's go ahead and take a look at an example of each. So let's say I'm looking at that reduction of iron 2 plus into iron. So let's say tap water has an iron 2 plus concentration, about 1 milligram per liter. So this is about 1.8 times 10 to the negative fifth molar. So this is a very normal sort of concentration of iron, especially here in the Midwest, where we tend to have a little bit irony water. So using the standard state reduction potential, what would I expect the actual reduction potential of my tap water to be? So let's go ahead and start by finding my Q. So again, products over reactants. So we're going to ignore electrons when we're looking at our Q. So solids, well, they don't show up. And reactant, well, it's the only thing there. And hey, we know its concentration, about 1.8 times 10 to the negative fifth molar. So this gives us a fairly large Q. And again, large Qs mean that we tend to be product favored. We essentially don't have nearly enough reactant. As I lower the amount of reactant, the reaction should become less favorable. Let's see how that works out. So we can calculate the potential, again, using our standard state value of negative 0.4. So we're starting unfavorable, and then we're subtracting out our relation constant. Now from here, the number of electrons being transferred is 2, and we know the reaction quotient. Plugging in those numbers, we start with an unfavorable reaction, and we're actually going to make it more unfavorable. So it turns out at such low concentrations, it would take a lot of energy to drive this reaction forward. It isn't exactly the most favorable system. So this is one of the reasons why iron ions don't usually suddenly form solid on your pipes. You need something to help encourage them to do so. Normally, the reaction is much more likely to go the other way as we rust your poor pipes. So one of the things that is worth noting, as we reduce the concentration, we make this forward reaction way less favorable, and by consequence, the reverse reaction way more. However, let's go ahead and see how this works if I'm looking at a full balanced cell reaction. So we've taken a look at this idea of zinc essentially reducing silver from silver +1 down to silver solid, and again, making that zinc 2+. So this has a measured cell potential of about 1.5 at standard state conditions. However, what would end up happening if I'm again trying to plate silver, and this is how a lot of silverware is made. You take steel and you put solid silver on the outside. So let's say what would happen if I start with a 2 molar silver nitrate concentration and 0.1 zinc sulfate. First thing to worth noting is that both of these are strong electrolytes, so I can ignore the counterions. Nitrate and sulfate won't play a big role here. So what I have is zinc 2+ gaining electrons and zinc losing electrons and silver gaining them. However, these are usually written as the reduction reactions. So that's essentially where those reduction potentials come from. So the most important thing about looking at these half reactions, though, is we will note that zinc is going to be losing 2 electrons and silver will be gaining 2 electrons. So 2 electrons are being transferred. Similarly, I can look at my original reaction to get the reaction quotient. Zinc is going to be my product and silver is my reactant, but watch out because there's 2 of them, so that'll play a role in the coefficient. So doing that, I now have my reaction quotient, and I know I'm transferring 2 electrons. We can plug those values into our Nernst equation. So we know the system starts out being fairly favorable, and we can then use our Q and our N to find the ending value. So we start with a favorable reaction. We essentially made it more favorable by adding additional reactants and reducing the amount of products. And so we essentially adjusted these concentrations, make the reaction slightly more favorable. We can get a little bit more energy out, and it will happen a little bit more easily. So next time, we're going to go ahead and take a look at how we can start applying these various electrochemical reactions into real use. Until then, take care.